Welcome to the third in a series of screencasts about reaction dynamics for the module CHE-30042. So today what we're going to do is we're going to talk about potential energy surfaces, and what I've done is I have identified a couple of opportunities for you to read about this outside of these screencasts. Both of these are available through the Bibliu textbooks function that you should be aware of already, and so you've got reaction dynamics by Brouard here, and this QR code should take you directly to the relevant pages. And likewise, there's computational chemistry by Jeremy Harvey, who incidentally was a lecturer in Bristol whilst I was a student, and taught me a bit about computational chemistry. So this book obviously comes at potential energy surfaces from a computational chemistry aspect, whereas this is perhaps a little bit more practical and theoretical. But in both cases, they're quite useful for just the basics and giving you another explanation of potential energy surfaces. Okay, so basically, why do we need a potential energy surface? Why can't we just use the tools that you're already aware of, like things like reaction coordinate diagrams? Well, let's just have a think about it. We'll consider this simple reaction that we've been using up till now. So A plus BC goes to our products AB plus C. And obviously these can be real species. So, for example, in the associated exercise for you that's associated with the screencast, I've got an example where it's hydrogen and HF reacting together to give H2 plus F. Yeah, it's the same idea. So what happens when these two react? Well, here we go. A is going to come in, it's going to form a new bond with B, and then the BC bond will break and C will go off. Yeah, so right, what can we do to think about the change in energy that's occurring through this process? Well, one thing we can do is we can plot the potential energy change as we get A is basically approaching BC. Okay, so on this one here we've got the Y scale is potential energy, and the X scale here will be the distance between the two species. So as A approaches BC, we're moving along this line, so potential energy will go down, and obviously as we get A starting to overlap with BC, it'll go up significantly. Okay, so that sort of tells us something, and it probably tells us something about the bond between A and BC, or A and B in this case. And this would be the equilibrium bond distance. But what it doesn't do is it doesn't say anything about the approach direction of A towards BC. So, for example, A could come from here and sort of attack BC, or it could come from up here and attack BC. How is the potential energy curve going to change in that case? It probably will change, but just one single curve can't tell us that, can it? So here we've actually got a curve plotted for the reaction as if it was coming from here. It's going to be different if it comes from here. The other thing it doesn't take into account at all is anything to do with the sort of products, so or the breaking of that BC bond. Okay, it doesn't tell us anything about that. In fact, it only tells us about these two species really. Okay, so we're missing a whole dimension here, and so already I think you can see that we can't take either of these things into account at all on a single diagram that's in 2 dimensions. Yeah, or not very easily anyway, not with just such a simple diagram. Okay, but of course we're quite familiar with the idea of 3 dimensions because we live in 3-dimensional space. So I mean, a very, very obvious example in this case would be we can go walking in the mountains, and you see the mountains in 3 dimensions, and all those dimensions are basically the Z direction. So the up direction is altitude, and then if we put ourselves on here, we can plot our position in terms of latitude and longitude. And again, we can use 2-dimensional diagrams, albeit 2-dimensional diagrams that are kind of special because they have contours on them that give us an idea of a 3rd dimension. So 2-dimensional diagrams that will give us a position here will give us a position in latitude and longitude, and then if we follow the contours we can get a rough idea of our altitude as well. Okay, so and what we want to do is actually use this kind of way of doing things to look at our reaction reactions perhaps in a bit more detail. And another thing you can do here is you can start plotting paths. Of course, I can plot paths through landscapes using maps. So if I want to find the easiest path to sort of get from one side of, in this case, Snowdon. So if we've got Penny Pass here, this is Snowdon here. This is the high point on this map. Okay. You've also got other high points like Krivgoch here, and you've got Penny Pass here. Now, Penny Pass is actually a high point in a valley, but if we start at Penny Pass and we want to get over here somewhere, then one way to do that would be to go up this way. We don't cut too many contours, it stays pretty flat, and then we have to just climb this last little bit here. Now, we don't go straight up to Snowdon because that would take us too high. The easiest way to do it is just to go up here, and then we can go down from there. Likewise, there might be another pathway which might lead us on this road here down in this direction too. So there are two ways to get to somewhere, and just like reactions where there are two ways to maybe go from a position, and in a reactions case this position will be a reactant, to products, and you might end up with different products if you follow this pathway versus this pathway. Okay, so what I'm trying to do here is using the analogy of maps and give you an idea of how we might go about if we have such a plot of our reaction that relates to our reaction. We can actually use it to get some information out, basically. Okay, so let's move back towards potential energy surfaces and away from 3D space and maps. So this is a typical potential energy surface. Okay, so what we have here is we're plotting 3 dimensions. We've got one dimension is our radius of A and B, so this would be the distance that A and B are apart, and so here at this origin point, then they are going to effectively be overlapping, and so you can think about what that means in terms of potential energy. And likewise, you've got BC here. So at this point in time, you've got BC overlapping. So, that would be pretty much infinite potential energy. And at this point out here, you've got BC very, very far apart. Okay. And likewise here is AB very far apart. And here on the diagram is everything is very far apart. So you've got A, B, and C all dotted very far apart from one another. And so let's think about potential energy. Well, if they're all overlapped, then that's going to be a very high potential energy because we can't overlap atoms, obviously. Or even if we get close to overlapping, then the electron spheres will start to repel very strongly, and so you get quite high potential energy there, so that's not favorable, so it's high. Okay, and likewise, if you have your things all very, very far apart, then you also have a high potential energy because you need a lot of energy to keep them apart, because as we well know, chemistry requires bonds to be made. Yeah, molecules and atoms like to be bonded with one another, so this is also a high energy point. So high potential energy here, high potential energy here. Of course, if you're here as well, that's high potential energy because you've still got 2 species overlapped, and likewise at this point here you've got high potential again because you've got A and B overlapped. Okay, so just starting to understand this diagram here, we have a very big distance between B and C. So they are, effectively apart, but you have a sort of close distance between A and B. Okay, so this would be our products, AB plus C. So C is far away, it's not attached. Yeah, and actually this point here where I've got my mouse now, this is basically roughly the equilibrium bond distance. Okay. So if you see this profile here, this is kind of the inverse of the Leonard-Jones potential that you should be relatively familiar with. And on the Leonard-Jones potential, the bottom of the potential well is the equilibrium bond length. And so just like here, the bottom of this potential well is the equilibrium bond length. Okay, and likewise here for the reactant. So here you have a big distance between A and B. So essentially your A and B are not bonded. C and B are close together because we're about here on that graph, and this point here is again the equilibrium bond length. Okay, key point here is that this potential energy surface doesn't contain any idea of this angle here. Okay, so what we'd have to do is we'd have to make new potential energy surfaces for each of these angles. So 0 degree or 180 degrees, 0 degrees, 90 degrees, etc. Yeah. The other important point there is that we've not just got one angle to make this 3 dimensions, have we? This one is an angle in one plane, which is the plane that's of my slide. okay? But there's also another angle that comes out of the slide towards you and me and describes the remainder of the 3D space. And of course, the position with relation to BC and the direction of approach is going to be given by both of those angles, okay? So that other angle is this one here called phi, okay, that I've not directly represented, but it does exist. But obviously in this case, phi is equal to 0 and this one is fixed for one surface. So you can start to think, well, I need quite a few surfaces to fully understand my reaction. But even with, say, 10 of these surfaces for different phi, different theta, you're going to start understanding how different positions of approach are going to make a difference, okay? And that's the point. We need loads of PESs to actually really build up a 3D picture. But we can start doing it with them. That's the point, really. Okay. Okay, so we need to think now about how to move through the potential energy surface, okay? So we've already said that this here is our reactants. So here we have BC together and A is far away, and this here is our products. But how do we move through the surface? And here I need you to think about, what might be happening here. And we have to visualize this as basically, in order to get from this point to this point, there's a valley here that goes through, and this place here right in the middle is slightly higher or higher than these points here in terms of potential energy, okay? And so we can draw a line which takes us the lowest energy pathway through here, and this line, which I've got given in green dotted line, here is representing that lowest energy reaction coordinate. And so, if you remember your reaction coordinate diagrams, this is that line, okay? Another key point is that on that line, you have the high point. And that high point we will refer to as either an activated complex or the transition state. And the transition state, this introduces this concept of a transition state, and I'll talk more about that sort of in next week's screencast when we start talking about transition state theory. But this transition state is essentially the high point on the lowest energy reaction coordinate. It's the saddle point on the potential energy surface. An analogy would be the mountain pass. If you're walking up, if you're trying to take the lowest altitude path, or the path that covers the least altitude, then you'd go through a mountain pass. And likewise, that mountain pass on a map, or that mountain pass on the ground, is the equivalent of that in a reaction space, is this transition state. Okay. So, moving on, we have other ways of depicting potential energy surfaces. The problem with the 3D potential energy surface is it's first of all pretty difficult to draw, and second most, it's not necessarily that easy to actually see where the high points are unless you're able to actually manipulate the 3D plot itself. So if you just hold it fixed, it's quite difficult to see things. Whereas with if we translate this detail to contours, just as translating the mountainous region to a map, then we can get the same information, or pretty much the same information out, but in a much easier to draw and potentially easier to analyze manner. Okay, so once again, this is a depiction of the potential energy surface I showed you a minute ago. It's tilted around a little bit. So previously this point here was the lowest point of the diagram before, and the origin is here. Okay, and then again we've got the same thing here. We've got the equilibrium bond lengths depicted here, and again this is the position in the well at either end of the diagram. Okay, and once again we have our lowest energy reaction coordinate, and you can see that because we start with the products, we start with the reactants here, we basically follow the lowest energy pathway, so basically that's going to cut the fewest contours possible. Okay, so we don't go this way because that would definitely lead to more contours being cut. We're going to go the most direct way that cuts the fewest contours. So here we go to here. This is the high point. So, we know that our reactants have lower energy than the center of the diagram. So this is the high point, and then from that high point, it drops away again, and we go to products. And in this case, the way I've depicted it, the products and the reactants have roughly the same potential energy, because we can tell that the same contours have been crossed here and here. Okay, so that's more information you can do. And if you want to think about a reaction, you could think about a ball rolling over this surface. And in this case, it's pretty easy to see what's going to happen because you have to just give the ball enough energy to get over this point here and therefore be able to roll down to this point here. And so again, back to reactants, you have to give the reactants enough energy to cross this point and get down there. What's the energy you have to give them? Of course, it's the activation energy. So, from this diagram, if we know what the potential energy of this point here is and the potential energy of this point here, then we can actually work out what the activation energy is. And we can certainly work out what the minimum activation energy is because we know we've crossed this contour and we know we've had to cross this contour. So the value in energy of this contour minus this contour gives us the minimum activation energy, if we don't know what the precise values here and here are. Okay. Great, so contour diagrams are essentially the same as the 3D plots, but it's just a bit easier to see what's going on, and it's like a map effectively. Okay, so here, for example, I've got very, very high radiuses on both sides, so my species are very far apart. Here they're overlapping, and along this line here, we're basically the BC distance is not changing, but A and B are getting closer together. Okay, so in other words, this is the reactants approaching the products. This is the reactants approaching one another, going this way. Okay, and likewise, this is the products moving away from each other, going this way. Okay, so just to sort of summarize, this is the sort of reaction coordinate diagram that you should be familiar with, where you've got your reactants, you've got your activation energy. The top point here is our transition state or activated complex, and then it falls down to the products. Now, this diagram here isn't quite a very good representation of this diagram because really the products and the reactants should have about the same energy, but nevertheless, you can rewrite this now as following this dotted line here is the equivalent of this dotted line here. Okay, and likewise you can do that in 3D too, but it's harder to see what's going on. And basically what I want you to do is to understand roughly how these might be put together. Okay, so potential energy surfaces, you can either construct them from experimental data, so where you've actually done some experiments. We'll talk a bit about what those experiments are in the next slide, or you can do this through calculation. So one example would be density functional theory, but there are many different calculations that you can do. Again, that book by Jeremy Harvey goes into that in some great depth that I don't require you to know for this course. However, what I would like you to understand is some of the techniques that you might be able to use to do this and sort of just understand the power of some of these techniques really. So typically what we're doing here is we're using crossed molecular beams. So what that means is you get a beam of reactants coming in and you would then fire another beam of the other type of reactant. So in this case, we have A and we have reactant BC. So my source 1 would have reactant A and my source 2 would have BC. And so for example, for the potential energy surface that we've got in the quiz that's connected to the screencast, source 1 would be hydrogen or H radical, or protons effectively, and source 2 would be HF in this case. Okay. And what you can do is you would fire this beam of molecules or beam of atoms, radicals, each other, and you make it so that they will cross one another. Okay, so that's where the cross molecular beams come in. And of course, if you can cross them and if you can shoot them from different angles, but also you can kind of select the energy with which you apply these beams. So you can energize the beams in various different ways. Okay, so you can control everything. And obviously, if you measure them with lots of different angles, lots of different types of energy beforehand, then you build up a very, very big picture of what's going on. And then you have a detector which is able to detect what's going on at this point where you actually have a reaction. Okay, of course, as we've already talked about, you've got one potential energy surface per direction of approach, also probably per other, per type of detector, etc. as well. So that's where the etc. comes in. And obviously this means that we need many different measurements. That makes sense, right? The way in which these products, which are evolved from the reaction that occurs here, can be measured is various advanced spectroscopy techniques, but they're very similar to the ones you're already familiar with. So you have mass spectrometry. Okay, so we can tell what the masses are of the products that are released. We have various types of chemiluminescence, and particularly infrared chemiluminescence, but not only that. I mean, what do you think infrared chemiluminescence is going to tell? Well, of course, it's going to tell us about bonds that are breaking or being formed within that species, but it can also tell us about how vibrationally active those species are too, right? And then, of course, we also have fluorescence, and so this would essentially give us an idea of the energy levels that are populated, okay? And particularly for fluorescence in sort of UV or visible regions, then that's going to be telling us about electronic energy levels, isn't it? Yeah, so there's a lot of different things we can use to detect. So this would be, more like your fluorescence spectroscopy that you're familiar with. This would be more like IR, and this is more like mass spec, but they're just a bit more advanced because they're able to do this over a very, very short time scale, for example, or they're able to do this with a very small amount of material. Okay. So we've got our techniques, we've built up our potential energy surfaces. What can we do with them? Well, once you've got a potential energy surface, you can actually use it to start making predictions, okay? And these predictions can be quite accurate. So for example, we've got the potential energy surface I showed you already, and basically what we can say is if we don't have enough energy to begin with, so if it's low translational energy but equally low any energy, then we're not going to be able to get as far as the transition state, and so therefore our reaction isn't occurring. So the analogy here would be you just haven't got enough activation energy. Yeah. If you have a high translational energy, then what might happen is you might overshoot the value of your transition state, cross another contour, and in doing so, what you do is you then set up this kind of flight path that does this. Now, if you think about this, RBC is still increasing, so essentially our products are moving away from one another, so the radius between B and C, or the radius between our products A, B and C, is increasing. But what is happening to the radius of AB? It's fluctuating backwards and forwards. Now this fluctuation backwards and forwards is a vibration. Basically A is getting closer to B, A is getting further away to B. Getting closer. So this representation here on a potential energy surface is a vibration, and it means that our products, our AB, are vibrationally excited. Okay. And likewise, if you start with our vibrationally excited reactants, you can actually get, again, it overshoots the transition state energy, and it will give us translationally excited products. So in this case, we end up with more energy going this way, and they will move away more effectively faster. Yeah. What else can you do? Well, we need to now think about different types of potential energy surface. So here we have what is described as a late transition state. Okay, so we have, whereas in the past we had a transition state down here, and that's kind of in the middle of the diagram, so that's neither early nor late. In this case, it's late because it's further towards the products along the lowest energy pathway, which is not this line here. It's the line that I'm making here with my dot. Okay. That would be the lowest energy pathway. It's closer to the products than it is to the reactants, and it's past the center line. That means it's a late transition state. Okay, and in this case, if you have vibrationally excited products, then you can follow this kind of line here, and you're going to end up with a reaction. Okay, but the issue here would be that because you have this effective potential energy wall, if you start with reactants that are translationally excited, then you may well hit that potential energy wall and just bounce straight off. So that gives you a kind of prediction that what might happen in terms of such a transition state. And likewise, you can do the same thing for an early transition state. If you have an early transition state, what might happen is you never quite get over that potential energy wall if you have a vibrationally excited reactants, whereas if they're translationally excited, they might just skip straight over it, and you'll end up with vibrationally excited products. Okay. So these are sort of vague predictions you might be able to make using these using these potential energy surfaces. Okay, some examples of real potential energy surfaces, and these are the ones that are in 3 dimensions in this case, but you've also got the contour plot underneath, and this is very similar to the one I showed you right at the beginning, and it makes sense that this one is a symmetrical potential energy surface because the reactants and the products are the same, right? And in this case, the transition state is right in the middle here. Okay, so this is an example for the simplest reaction, and something that might surprise you is when this paper was published, only 9 years ago. Okay, so this stuff is actually really quite recent. What we're talking about here. This one here is an interesting one because you are starting up here on the diagram in this case. Okay, so we've got our reactants here. These are our reactants here, and that's because our RCO is low, whereas our RHO is big. Okay, so we start here, and what we can do is we can go this way via here to here. But what we have to here is 2 transition states. Okay, yeah. So there's a transition state here and a transition state here, and here we have a potential energy well. Okay, and that potential energy, we know it's a well because this contour is clearly below this contour. Yeah, because you can kind of see again, you're crossing the contours here, but it's below this one. Yeah, so you can see this is a well. It could also, of course, be a peak, but that's very unlikely in a diagram. And normally what we'd have is contour values that mean we know it's not a peak. But this is a well, and that well is an intermediate. Because a well has to be an area in which the potential energy is lower than it is at the transition state, and so if you drew a reaction coordinate diagram here, you'd end up with 2 humps effectively. So in the middle of those humps would be the intermediate, which is HOCO. And again, because you've got 2 humps, you've got 2 transition states and effectively 2 activation energies. Okay. Of course, we're not always talking about simple processes, and this is an example of a potential energy surface of a more complex process. And here we get back towards what we talked right at the start, where I said there's all these different pathways of getting up a mountain or getting to the other side of a mountain. And just like you have lots of different pathways in a reaction, you have lots of possible products, and or maybe even 2 ways to get to the same products. Okay, so here, for example, if you start here, reactant, you've got a minimum for reactant, you can go this way and you end up in product A. You can go this way, you end up in product B. Okay, and this is the transition state for that type of reaction. This is the transition state for that type of reaction. And again, you'd know then that if you operate under conditions that have a higher amount of energy available, then you might be able to access this reaction. Whereas if you operate under conditions where activation, the amount of energy you've got is lower, so the temperature is lower, you might only get product A. So, this is actually, you could already think, well, I know some examples of some reactions where I need to control the temperature. This is why, yeah? Okay. And this relates back to the mechanism. Okay, so just to summarize, potential energy surfaces, they're a very powerful way to to understand more about the reactions, and we can determine several things by just basically directly looking at them. Okay, and certainly, I'll expect you in associated exercises to be able to determine some of the listed factors that I have here. And the final point about potential energy surfaces is obviously, each of these represents one single approach direction, and that there are multiple approach directions. So obviously, in order to understand a reaction in full, we need to consider many different approach directions. And so you need a lot of different potential energy surfaces in order to do that. So thanks very much for listening, and please now try the little test I have on the KLE for you.